my name is Katie Allen, and my poster presentation discusses quantifying upper body postures with a motion sensing garment. Upper extremity musculoskeletal disorders occur at high rates within the workplace. Force, frequency, posture, and duration of a task all play a role in the determination of musculoskeletal injury risk. Currently, there are no standard ergonomic monitoring systems that identify poor postures and hazardous movements in workers. So there's a need for a non-optical wearable option for evaluating and monitoring ergonomic posture in the workplace. A motion sensing garment is a lightweight garment that can be worn over or under an individual's work clothes. The garment is instrumented with 7 inertial measurement units, or IMUs, 1 on each arm and forearm, and 3 positioned down the spine. The MSG enables the quantification of torso, shoulder, and elbow angles, which can be used to inform ergonomic assessment models like RULA. The goal of this study is to compare the postures measured by the MSG to the Vicon motion capture system. Analyses are focused on a comparison of ergonomic joint angles with an overarching objective to quantify the reliability and accuracy of the MSG as an option for non-invasively quantifying hazardous postures in the workplace. So 6 participants were subsampled for this analysis. Data were recorded simultaneously by the MSG and Vicon. The 3 movements chosen for analysis were elbow sagittal flexion, elbow transverse flexion, and elbow external rotation. Vicon data were post-processed in V3D, and IMU data were processed using custom algorithms written in Python. Primary analyses were run using one-dimensional statistical parametric mapping, or SPM. SPM analyzes waveform data over time with a series of paired t-tests to identify differences in signals, and it has the ability to differentiate at what time point significance was reached. Figure 1 here shows the placement of the IMUs in the MSG, and Figure 2 shows the placement of the retroreflective markers for the Vicon system. Moving on to the results, Figure 3 shows an example of a full movement trial. So for the chosen movements, the action was repeated 3 times, as you can see by the 3 cycles in the plot. Data was time synchronized and then split into single repetitions indicated by the dashed lines. Each cycle was then standardized to a specific number of frames, and the average was taken of the 3 cycles. In figures 4 and 5, you can see the plotted results of the SPM analysis. This output is a comparison of all 6 subjects performing the same movement with the same joint and direction being compared. On the left in figure 4, you can see an example of when the 2 systems are tracking well with each other. This is for a primary joint in the primary direction, so in this case it's elbow and flexion. The left graph shows the average joint angle of all the subjects, and the graph on the right shows the results of the SPM analysis. They follow the same waveform pattern and visually appear to be reporting similar values, but you can see it dips just below the critical t value, indicating significance with the p-value shown. On the right in figure 5, you see an example of the 2 systems not tracking well with each other. This is for a primary joint in a non-primary direction, in this case, elbow and abduction. Table 1 summarizes the SPM results for all joints in their primary directions. The top number is the p-value reported, and the bottom number shows the associated root mean square error. As you can see, some of the errors are quite high. Significant results are shown in bold, but even non-significant results can still have a high difference in angle measurements. So ultimately, wearable garments like the MSG have potential to accurately monitor kinematics and identify hazardous postures in the workplace. However, more investigation needs to be done to fully determine its capabilities. Sources of error could be coming from the sensors themselves, from potential time misalignment, calibration poses used by each system, or even improper sizing of the shirt. When processing the IMU data, a calibration pose was defined for each movement, whereas in the processing of the Vicon data, a single calibration pose was calculated for each subject and used for all movements. Differences in these calibration poses could contribute to the errors we see. There are also potential errors originating from the processing of the data. IMU data and the motion capture data were processed by 2 different algorithms, which could add to the error. These will continue to be investigated moving forward. A wearable system like the MSG could help provide knowledge about how the posture, frequency, and duration of movements contribute to workplace musculoskeletal disorders. This technology would offer a non-optical and non-invasive solution for ergonomic monitoring in the workplace. And outside of occupational biomechanics, this wearable garment could also have an impact in rehabilitation, at-home physical therapy, and athletic training. Thank you for listening.